Welcome to the Nocturnal Astronomer, where we journey through the cosmos to explore the most profound mysteries of our universe. I'm your host, Atlas Reid, and tonight we embark on perhaps the most mind-bending exploration of all, the very edge of everything we can possibly know. Imagine standing at the shore of an infinite ocean, knowing that somewhere beyond the horizon lies a boundary you can never cross. Tonight we venture to the cosmic horizon, that ultimate frontier where space and time began, where light itself has not had enough moments to reach us since the beginning of existence. We'll discover why this boundary exists, what it tells us about the nature of reality itself, and why it represents both the limit of our knowledge and the greatest testament to our cosmic heritage. If you enjoy these cosmic journeys through the mysteries of our universe, give this video a thumbs up and subscribe for more nocturnal adventures among the stars. And here's something fun. Tell me in the comments about the most distant object you've ever seen with your own eyes, whether it's the moon, a planet, or even the Andromeda galaxy. Alright, let's dive in. All objects we observe today lie inside what astronomers call the particle horizon, which forms the boundary of the observable universe. If an object lies beyond this particle horizon, then the universe is not old enough for its light to have had enough time to reach us. Think of this cosmic boundary like an enormous sphere surrounding us in every direction, but it's not made of any physical material. Instead, it's made of time itself. Picture yourself in a vast theater where the lights have just been turned on after being dark for countless eons. The light from the stage reaches your eyes almost instantly, but light from the back row takes a fraction longer. Now imagine this theater is so enormous that even traveling at the speed of light, some illumination from the furthest seats hasn't reached you yet. This is exactly what happens on a cosmic scale. Our universe is approximately 13.8 billion years old, which means we can only see objects whose light has had that much time to travel to us. This creates what we call the observable universe, a sphere roughly 28 billion light years across, with Earth sitting right at the center. But here's where it gets fascinating. This isn't because we're special or located in some privileged position. Every observer in the universe sits at the center of their own observable sphere. The boundary isn't a wall in the traditional sense. There's no cosmic construction material blocking our view, no galactic curtain hanging in space. Instead, it's a horizon of information, a limit imposed by the fundamental nature of light and time. Beyond this boundary, galaxies, stars, and entire cosmic structures may exist, but their stories remain forever hidden from us. Their light simply hasn't had enough time since the Big Bang to complete its journey to our telescopes. What makes this boundary even more intriguing is that it's not static. This expansion means that the cosmic horizon is not a fixed boundary, but a dynamic limit that changes over time. Every second that passes, light from slightly more distant objects crosses this threshold and becomes visible to us for the first time. Our universe is constantly revealing new chapters of its story, one photon at a time. This cosmic horizon represents one of the most fundamental limits in physics. Unlike barriers we might encounter on Earth, this one cannot be overcome through better technology or more powerful rockets. It's woven into the very structure of space-time itself, a boundary that emerged from the moment our universe began its expansion from that initial, incomprehensibly hot and dense state we call the Big Bang. The most remarkable thing about our cosmic boundary isn't what lies beyond it, but what we can actually observe at its edge. The cosmic microwave background is the cooled remnant of the first light that could ever travel freely throughout the universe. This fossil radiation was released soon after the Big Bang. When we look toward the edge of our observable universe, we're not peering into empty space, but rather witnessing the afterglow of creation itself. Imagine the early universe as a thick fog so dense that light couldn't travel more than a tiny distance before hitting something. For the first 380,000 years after the Big Bang, the universe was filled with a hot plasma where photons constantly scattered off free electrons, creating a cosmic soup that was completely opaque. Then something extraordinary happened. As the universe expanded and cooled, electrons and protons combined to form the first hydrogen atoms, and suddenly the fog cleared. Light could finally travel freely through space. This moment, called recombination, marked the universe's transition from opacity to transparency. The light that was released during this cosmic dawn is what we observe today as the cosmic microwave background radiation. This very uniform glow of microwaves was emitted by the infant universe more than 13 billion years ago. Every direction we look in the sky, we see this ancient light, cooled and stretched by billions of years of cosmic expansion. Think of it like looking at the surface of the sun, but instead of seeing the surface of a star, we're seeing the surface of the entire universe at its moment of transparency. This radiation fills every cubic centimeter of space, a constant reminder of our cosmic origins. Radio telescopes detect approximately 400 photons of this primordial light in every cubic centimeter of empty space, making it the most abundant form of radiation in the universe after starlight. The temperature of this cosmic afterglow tells us an incredible story. Today it measures just 2.7 degrees above absolute zero, but when it was first released, it glowed at a temperature of about 3,000 degrees. The dramatic cooling occurred because the expansion of space itself stretched the wavelengths of these ancient photons, shifting them from visible light into microwaves. This stretching is like a cosmic Doppler effect, where the expansion of space itself redshifts the light. According to the Planck mission data, the age of the universe is 13.8 billion years old, and this ancient light provides our most precise measurement of that age. The patterns and tiny temperature variations in this background radiation act like fossilized sound waves from the infant universe, preserving information about the density and composition of matter in those earliest moments. These fluctuations, smaller than 1 part in 100,000, were the seeds that eventually grew into galaxies, stars, and everything we see today. To truly understand our cosmic boundary, we need to grasp how space itself behaves on the largest scales. The universe isn't expanding into some pre-existing empty space, rather space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. This expansion creates some of the most counterintuitive phenomena in all of physics, fundamentally altering how we think about distance and time on cosmic scales. Consider two galaxies separated by a vast distance. If space between them expands, they move apart without actually traveling through space. They're carried apart by the expansion of space itself. This might seem like a subtle distinction, but it has profound implications for what we can observe. Some regions of space are now moving away from us faster than the speed of light due to this expansion, making them forever unobservable from Earth. This creates what cosmologists call the cosmic event horizon, which is different from our particle horizon. While the particle horizon represents the distance light has traveled since the Big Bang, the event horizon represents the boundary beyond which events happening now will never be observable to us, no matter how long we wait. It's roughly 16 billion light years away, and galaxies beyond this distance are receding so quickly due to cosmic expansion that their light will never catch up to us. Picture yourself on a giant cosmic treadmill that's speeding up. Even if you run towards someone ahead of you, if the treadmill itself is moving backwards, you'll actually move further apart despite your efforts. This is what happens to light from very distant galaxies. The photons race toward us at the speed of light, But space expands so rapidly between us and those distant sources that the light gets carried further away even as it travels in our direction. The geometry of space itself plays a crucial role in these cosmic boundaries. Current observations suggest our universe is geometrically flat, meaning parallel lines remain parallel and the angles of triangles add up to 180 degrees, just as they do in everyday Euclidean geometry. However, this flatness extends only across the observable portion of the universe. The global geometry of the entire cosmos remains unknown and might be fundamentally unknowable. This flat geometry has important implications for infinity. In a flat, infinite universe, every possible arrangement of matter and energy would repeat infinitely many times. There would be infinite copies of our galaxy, our solar system, and even infinite versions of you. However, these cosmic duplicates would lie far beyond our observable horizon, separated by distances so vast that no information can ever travel between them. The cosmic boundary thus becomes a fundamental limit not just on what we can see, but on what can causally influence us. The question of what exists beyond our cosmic horizon represents one of the deepest mysteries in all of science. By definition, we cannot observe anything beyond this boundary, yet theoretical physics provides several compelling possibilities for what might lie in those unreachable regions. Each scenario carries profound implications for our understanding of reality itself. According to one theory, the universe extends infinitely in all directions. In an infinite universe, our observable region would represent an infinitesimally small fraction of the total cosmos. Beyond our horizon, galaxies, stars, and planetary systems would continue indefinitely, following the same physical laws that govern our local cosmic neighborhood. The cosmic microwave background would extend everywhere, and the same processes of star formation and galactic evolution would play out across boundless space. An infinite universe raises fascinating questions about repetition and uniqueness. In truly infinite space, every possible arrangement of matter would occur not just once, but infinitely many times. This means there would be perfect copies of our galaxy located at unimaginably distant locations, complete duplicates of our solar system, and even exact replicas of Earth with identical histories. These cosmic twins would exist beyond our causal horizon, forever unreachable yet identical in every detail. The multiverse theory assumes that there are many universes that may have different properties. Our cosmic horizon might represent just the boundary of one universe among countless others, each with potentially different physical constants, laws of nature, and evolutionary histories. Some of these parallel universes might have stronger or weaker gravity, different values for the speed of light, or alternative configurations of fundamental particles that lead to entirely different forms of matter and energy. Another possibility involves curved spacetime. Space can be closed, like the surface of a sphere returning to the initial point. If our universe has positive curvature, it might wrap back on itself like the surface of a hypersphere. In such a universe, if you could travel far enough in any direction, you would eventually return to your starting point, similar to how you can circumnavigate the Earth. Our cosmic horizon would still exist due to the finite age of the universe, but beyond it would lie more regions of the same universe, possibly including distant views of our own cosmic neighborhood. Perhaps most intriguingly, some theories suggest our entire universe might exist within a higher dimensional structure. The hypothesis states that our universe in general may be part of a black hole in another dimension. In this scenario, what we experience as the Big Bang and cosmic expansion might be the formation and growth of a black hole as viewed from a higher dimensional perspective. Our cosmic horizon would then represent a boundary in this higher dimensional space, beyond which lie realms operating under completely different physical principles. Each of these possibilities reminds us that our cosmic boundary represents not just a limit on observation, but a fundamental constraint on knowledge itself. Our cosmic boundary isn't frozen in place, it's constantly evolving as the universe ages and expands. Understanding how this horizon changes over time reveals the dynamic relationship between cosmic expansion, the speed of light, and the ultimate fate of our observable universe. This evolution tells a story of both revelation and loss, as new regions come into view while others slip forever beyond our reach. Every second, light from objects roughly 300,000 kilometers further away crosses our particle horizon for the first time, adding new volume to our observable universe. This might seem like we're constantly expanding our view of the cosmos, and in one sense we are. Previously invisible galaxies and cosmic structures continuously emerge from beyond the horizon, their ancient light finally completing journeys that began billions of years ago. However, the story of our expanding view is complicated by the acceleration of cosmic expansion. Observations of distant supernovae revealed that the expansion of space is actually speeding up, driven by a mysterious force cosmologists call dark energy. This acceleration means that while our particle horizon grows larger, our event horizon, the boundary of what we could ever hope to see, actually shrinks. The cosmic microwave background provides a perfect example of this evolution. The radiation we observe today was emitted when the universe was only 380,000 years old, from a region that was then about 42 million light-years away from the matter that would eventually become our galaxy. However, due to cosmic expansion, those same regions are now estimated to be about 46 billion light-years away, well beyond what we might naively expect for a 13.8 billion-year-old universe. As we look toward the far future, the cosmic horizon will continue its complex dance of expansion and limitation. In the very distant future, perhaps 100 billion years from now, the accelerating expansion will have carried most galaxies beyond our event horizon. Future astronomers in our galaxy will observe a much lonelier universe, with only the galaxies in our local cluster remaining visible. The cosmic microwave background will have cooled and faded, and the evidence for the Big Bang itself may become difficult to detect. This evolutionary perspective adds a poignant dimension to cosmology. We exist during a special epoch when the universe is old enough to have developed complex structures like galaxies and stars, yet young enough that we can still observe the cosmic microwave background and distant galaxies that tell us about cosmic history. Our position in time is as privileged as our position in space for understanding the cosmos. Determining the exact size and properties of our cosmic horizon represents one of the greatest measurement challenges in science. Unlike distances we can measure with rulers or even radar, cosmic distances require ingenious methods that push the boundaries of observational astronomy. Each technique reveals different aspects of our cosmic boundary while highlighting the profound difficulties of measuring the unmeasurable. Astronomers use what they call the cosmic distance ladder, a series of interconnected measurement techniques that allow us to gauge distances across increasingly vast scales. It begins with parallax measurements of nearby stars, where we observe how their positions shift as Earth orbits the Sun. This provides direct geometric distances to stars within a few hundred light years, creating the foundation for all other cosmic distance measurements. The next rung involves Cepheid variable stars, whose brightness pulses in a predictable pattern related to their intrinsic luminosity. By measuring how bright these stars appear compared to how bright they actually are, astronomers can calculate their distances. This technique extends our reach to nearby galaxies, including the Andromeda Galaxy and other members of our local galactic neighborhood. For the most distant objects near our cosmic horizon, astronomers rely on Type 1a supernovae, thermonuclear explosions of white dwarf stars that reach nearly identical peak brightness. These cosmic lighthouses can be seen across billions of light years, allowing us to measure distances to galaxies when the universe was much younger. The observations of distant supernovae in the 1990s revealed that cosmic expansion is accelerating, fundamentally changing our understanding of the universe's fate. The cosmic microwave background provides our most precise tool for measuring cosmic parameters. Tiny temperature variations in this ancient light create patterns across the sky that depend on the fundamental properties of the universe, including its age, composition, and geometry. The Planck mission measured the age of the universe as 13.8 billion years old, providing our most accurate determination of when cosmic time began. However, measuring our cosmic horizon involves more than just distance. Because space itself expands, we must carefully distinguish between different types of distances. The light travel time distance tells us how long light has been traveling to reach us. The comoving distance accounts for how far objects have moved due to cosmic expansion since they emitted their light. The angular diameter distance describes how large objects appear in the sky, while the luminosity distance determines how bright they appear. These multiple distance definitions create a complex picture of cosmic geometry. An object whose light has traveled for 10 billion years is not necessarily 10 billion light years away today. Due to cosmic expansion, it's actually much further. This expansion also means that the most distant objects we can observe emitted their light when they were much closer to us than they are now. Recent measurements have revealed tensions between different methods of determining cosmic distances and expansion rates. These discrepancies, sometimes called the Hubble tension, suggest either systematic errors in our measurements or new physics beyond our current understanding of cosmology. Resolving these tensions remains one of the most important challenges in modern astronomy. Our cosmic horizon represents far more than just an observational limit. It embodies fundamental truths about the nature of reality, causality, and our place in the cosmos. The existence of this boundary raises profound questions about knowledge, infinity, and the very meaning of existence on the largest possible scales. Understanding these implications transforms how we think about everything from physics to philosophy. The horizon creates what physicists call causal disconnection. Events occurring beyond our cosmic boundary cannot influence us in any way, nor can we affect them. This isn't simply a matter of current technological limitations, it's a fundamental feature of spacetime itself. Two regions of the universe separated by more than the horizon distance exist in complete causal isolation, as if they were separate universes entirely. This challenges our intuitive notion that all of space is somehow connected and unified. Consider the implications for the nature of physical laws. We observe that physics appears remarkably uniform across our observable universe. The same atomic spectra appear in galaxies billions of light years away, suggesting that the fundamental constants of nature are identical everywhere we can look. But what about beyond the horizon? We have no way of knowing whether the same laws apply in those unreachable regions. The cosmic boundary thus represents the limit of empirical science itself. The horizon problem in cosmology illustrates these deep puzzles. Different regions of the cosmic microwave background, separated by angles larger than about 2 degrees on the sky, were never in causal contact during the early universe. Yet these regions show nearly identical temperatures, as if they somehow coordinated their properties despite never being able to exchange information. This puzzle led to the development of cosmic inflation theory, which proposes that the early universe underwent a brief period of exponential expansion that brought distant regions into causal contact before stretching them beyond the horizon. Our cosmic boundary also illuminates questions about infinity and uniqueness. If the universe extends infinitely beyond our horizon, then every possible configuration of matter and energy occurs infinitely many times. This includes exact duplicates of our galaxy, solar system, and even ourselves. But if the universe is finite, we might represent truly unique arrangements of matter and energy. The cosmic horizon prevents us from ever knowing which scenario is correct. The concept of cosmic horizons also appears in other areas of physics, most notably in black hole physics. Black holes have event horizons beyond which nothing can escape, creating boundaries that are remarkably similar to our cosmic horizons. Some physicists suggest deep connections between these different types of horizons, hinting at fundamental principles that govern the flow of information in the universe. The holographic principle proposes that all information contained within a volume of space can be encoded on its boundary, suggesting that our three-dimensional reality might somehow be encoded on our cosmic horizon. Perhaps most remarkably, our cosmic boundary serves as a mirror reflecting our own significance and limitations. We exist as conscious observers in a universe vast beyond comprehension, capable of contemplating boundaries we can never cross. The very fact that we can conceive of and study our cosmic horizon represents one of the greatest achievements of human curiosity and intelligence. We have used mathematics, physics, and careful observation to map the unmappable and measure the unmeasurable. As we reach the end of our journey to the edge of everything, we find ourselves confronting the most profound boundary in existence. The cosmic horizon stands as both a wall and a window, limiting what we can know while revealing the magnificent scope of cosmic history. This invisible boundary, forged in the first moments after the Big Bang, continues to evolve as our universe expands and ages, constantly reshaping our view of reality itself. We've discovered that our cosmic horizon isn't simply empty space waiting to be explored, but rather the afterglow of creation itself, preserved in the ancient light of the cosmic microwave background. We've seen how the expansion of space creates multiple types of horizons, some bringing new regions into view while others carry distant galaxies forever beyond our reach. We've explored the profound challenges of measuring distances on cosmic scales and the deep implications of living in a causally bounded universe. Perhaps most importantly, we've learned that the cosmic horizon represents the ultimate expression of both our capabilities and our limitations as conscious beings. Through careful observation and brilliant reasoning, we've mapped the boundary of the knowable universe, yet that very boundary reminds us that some questions may forever remain beyond our reach. The horizon humbles us while simultaneously celebrating the remarkable fact that we can contemplate such vast scales at all. In the end, the edge of everything teaches us that we inhabit a universe of breathtaking scope and beauty, one where the journey of discovery is as important as any destination. Every photon that crosses our cosmic threshold carries with it a story from the deep past, connecting us to the very origins of space and time. And on that note, we conclude our exploration of the universe's ultimate boundary. Thank you for joining me on this cosmic journey to the edge of everything. Until next time, keep looking up, and remember that we are all travelers together on this pale blue speck, surrounded by the infinite mystery of the cosmos.